Good afternoon, grade 12 learners. Welcome to today's chemistry lesson for grade 12. My name is Thandwe Uwane. This lesson is proudly brought to you by Gauteng Department of Education in collaboration with Saibono Discovery Center and streamed by Phakama Research and Development. Remember, this lesson can be interactive by using our WhatsApp number, which is 064 748 8913. We will try by all means, as I always promise, to come back to your questions or your opinions that you have in terms of every interaction that we are going to have in this lesson. Our today's lesson is based on chemical equilibrium. This lesson actually is coming from the previous lesson that we did in our previous week on chemical reactions. As I promised that we are going to continue for this week looking at chemical equilibrium. The previous lesson was looking at the reactions where we're having an open system, meaning that we're looking whereby the reactants were going into completion or the reactants were used up. However, today's lesson is going to look at a process whereby now our reactants are not going to be used up, but they are going to reach equilibrium. Now, let's look at the objectives of the lesson. On the objectives of the lesson, we are going to look at the explanation of open and closed system. This is an expectation according to our exam guideline. We are also going to look at reversible reactions and chemical equilibrium. The chemical equilibrium is already provided a definition for you on your exam guideline. So what do you mean by a chemical equilibrium according to the expectations of the exam guideline? It is a dynamic equilibrium when the rate of the forward reaction equals to the rate of the reverse reaction. So already the exam guideline has provided you with the definition of chemical equilibrium. We are also going to look at the factors that influence the position of an equilibrium. And those factors are going to be the pressure for gases only, concentration, and temperature. We are also going to look at the equilibrium constant. We are going to list the factors that influence the value of the equilibrium constant, which is Kc. Write down an expression for equilibrium constant having been given equation for the reaction. Perform calculations based on the Kc values. Remember, Kc is a symbol for equilibrium constant. So we are going to perform calculations on Kc values. And when we are also going to look at and explain the significance of the high and the low values of equilibrium constant. And we are also going to look at the application of equilibrium principles, which is going to be the Le Chatelier's principle. So we are going to be expected to state Le Chatelier's principle. We are also going to use Le Chatelier's principle to explain changes in equilibria qualitatively and interpret graph of equilibrium, example, concentration, rate, number of moles, mass, volume versus time graphs. And we are also going to explain the use of equilibrium, explain the rate and equilibrium principle in the Haber process and in the contact process. Now, as we are going to start our lesson for today, our expectation is to understand what we mean by an open and a closed system. As I said that in our previous lesson, we looked at the reactions that occurred at an open system whereby reactants were used up. However, this time we are going to look at the reactions that reaches equilibrium whereby reactants are not going to be used up. So what do we mean by an open system? It's a state of a system in which the system continuously interactive with its environment, meaning that reactants or product may enter or leave the reaction container. If you are having a system which is an open system and whereby you are having a reaction, you will expect the reactants or products to enter or leave the system, meaning that the system interact with its environment. The system can be in an open container whereby reactants can move out and in of the container. Now we are going to look at a closed system. It's a system in the state of being isolated from its environment, meaning that no chemicals is allowed to enter or leave the reaction. This is the system that we are going to look at in our current lesson, because the system that you are going to look at, you are going to look at the reaction that occur in a closed system, whereby the system is being isolated from its environment, meaning that our reactants and our products cannot enter or leave the system. They are said to be in a closed system or isolated system. Now, let's look at type of reactions. We have irreversible reactions and reversible reactions. What do we mean by irreversible? The word can explain itself. Irreversible means that the system or the reaction takes place in only one direction. The examples that I was providing in my previous lesson were the reactions that were only moving in one direction only, meaning that those reactions were irreversible. I couldn't make the products to form back the reactants, meaning that immediately when the reactants formed the product, the reactants were going to be used up. So in those systems, we were using, let me just indicate, we were using a single arrow which is facing forward, which was representing that our system was moving in only one direction. But now, what do we mean by reversible reactions? Because reversible reactions are the ones that we are going to look at more often today as we are going to discuss our chemical equilibrium. The product can change back to the reactants, meaning that as the reactants are going to form products, the products can go back and form reactants. And we are using this double arrow to show that our reaction is reversible. So it is very important that you understand what is meant by irreversible reactions and what is meant by reversible reactions. Irreversible, it is moving in one direction only, meaning that is only going to forward reaction. However, when we look at irreversible reaction, we are going to look at both forward and reverse reaction. It is very important that you understand the word reverse and reversible, because when I say reverse, I mean backward. However, when I say reversible, I mean forward and backward. So the two words must be used very carefully, because sometimes you can confuse the two words thinking that when you are saying reverse, you mean reversible. Reversible is forward and backward. However, reverse, it means backward only. Now, these are the two reactions that we have to look at, which is reversible and irreversible reactions. The next thing that you need to talk about, we need to talk about the two types of reactions or the systems, which are homogeneous and heterogeneous reactions. What do you mean by homogeneous reactions? When you look at the homogeneous reactions, we look at the systems that have the same phase, meaning that the reactants and the products will have the same phase. If they are gases, they will all be gases. If they are aquas, they will all be aquas. For example, if I'm having a reaction like I'm having hydrogen gas reacting with nitrogen gas to give me ammonia, which is also a gas, then I can safely say all the reacting particles or all the reacting substances are in a form of a gas. So I can safely say this is a homogeneous reaction. What do you look at? You only look at the phases of your reactants and your product. If all of them are in a same phase, you will refer to them as a homogeneous system. But now let's look at heterogeneous. What do you mean by heterogeneous? Let's say I have calcium carbonate that decomposes to, this one can be reversible reaction, that can decompose to calcium oxide and carbon dioxide. Calcium carbonate is a solid. Calcium oxide is a solid. However, carbon dioxide is a gas. If you look at the phases of my reactants and my products, you can see that they are not all in the same phase. Some are solid, some are gases. Therefore, we refer to them as a heterogeneous system because their phases are not the same. So an examiner sometimes can ask you whether the system or the reaction is homogeneous or heterogeneous. what is it that you must look at? You must look at the phases or the states of those reactants and the products to say if they are all in the same phase, it means they are homogeneous. If they are in different phases, it means they are heterogeneous. Now, what do we mean by equilibrium expression? I think by now we have tried to define equilibrium constant, chemical equilibrium. And we said chemical equilibrium will be reached where we find the rate of forward reaction being equal to the rate of reverse reaction. Now, equilibrium expression. We are going to use an expression to calculate equilibrium constant. Now, what do we mean? I think you have seen that I'm having my reversible arrows, meaning that the forward reaction can also form a reverse or backward reaction, meaning that the reactants can be converted to products and products can be converted back to reactants. We must not forget what we explained in our previous reactions, whereby we were looking at products being formed whereby the reactants concentration was decreasing. The products were only forming when the concentration of the reactants was decreasing. And as the concentration of the reactants was decreasing, the concentration of the product was increasing. So it is very important to understand that immediately when the reaction starts, the concentration of the reactants or the volume or the mass of the reactants will definitely decrease as the mass of the product starts to increase. Now, when you look at the reaction that I'm having in front of you, I'm having a reaction between A and B, where we have number of moles of A reacting with number of moles of B. I think we already understand that N and M represent the number of moles of those reacting substances. So the number of moles of A will react with the number of moles of B to give you the X number of moles of C and Y number of moles of D. We know that our A and B are our reactants and our C and D are our products. But by looking at our reversible arrows, we know that AB can form CD and also CD can form AB. Now, A and B can react to form C and D, or in this reverse reaction, C and D can react to form A and B. So we can proudly say this is a reversible reaction, because as reactants can form products, products can also go back and form reactants. That is very important. You need to know that in terms of the reversible reaction, the forward reaction can also be changed to become a reverse reaction. And I was saying reversible reaction, meaning that it can be forward and also reverse reaction. Now, chemical equilibrium involves the balancing of two reactions which are occurring at the same time in opposite direction. It is said to be dynamic equilibrium. That is, it is equilibrium involving constant interchanging of particles in motion, meaning that at a certain stage, our forward reaction and our reverse reaction will have the same concentration and they will occur at the same rate. And at that state, we say the reaction hasn't stopped. That is why we use the word dynamic. Dynamic means the reaction hasn't stopped. However, the rate of forward reaction is equal to the rate of reverse reaction. What do you mean by chemical equilibrium? As we are going to recap, chemical equilibrium is when the rate of forward reaction is equal to the rate of reverse reaction. The word rate is very important when you give this definition. It's not forward reaction being equal to reverse reaction. However, it is the rate of forward reaction being equal to the rate of reverse reaction, meaning that the two reactions occur at the same rate. Therefore, when you explain what you mean by chemical equilibrium is when the rate of forward reaction is equal to the rate of reverse reaction. The word reverse, as I was emphasizing, it must not be confused with the word reversible, because reverse means backward. I will try by all means to be as slow as possible, and to explain this concept as slow as possible, so that at the end of the day, you know the contradictions that might come about in terms of these terms, because sometimes you will feel that they are the same, whereas they are not. So as I was explaining, to say is the rate of forward reaction being equals to the rate of reverse reaction, and these reactions are said to be reversible reactions, and is when we reach chemical equilibrium. Now, as I explained in on my previous slide, to say dynamic means the reaction does not stop. However, the rate of forward reaction is equals to the rate of reverse reaction. And as you are looking at the reaction with your eyes, you will think that the reaction has stopped, whereas the reaction hasn't stopped, but the reaction has reached dynamic equilibrium. Now, let's look at the example that is provided in front of us. This is an example of the reaction between hydrogen gas and iodide vapor, giving you hydrogen iodide. Immediately when you look at the faces of all the reactants and the product, you can see that these reactants and the products they are all gases, meaning that they are all having the same face. So the first thing that you ask yourself is that, is this a homogeneous or a heterogeneous system? And the next thing, you can see that we are having our reversible arrows, meaning that this reaction is reversible, meaning that the hydrogen and iodide and iodine can react to form hydrogen iodide, and also hydrogen iodide can also react back and form hydrogen and iodide in a vapor. Now, hydrogen gas and iodide vapor are mixed in a closed container. A reaction proceeds. As the reaction proceeds, the concentration, that is very important, the concentration of hydrogen and iodine decreases. This is exactly the same as what we explained in our previous lesson, to say immediately when the reaction starts, or immediately when we start the reaction, what is going to happen? We are going to expect the concentration of the reactants to decrease. And exactly what we explained previously is happening even now. The concentration of the hydrogen and the iodine, because they are both our reactants, will decrease. And the rate of forward reaction will also decrease. Meaning that as the reaction will start, we'll expect the rate of forward reaction to decrease as the concentration of the reactants is decreasing. Then the rate, and then the concentration of hydrogen iodide increases, and the rate of reverse reaction will increase. Remember, as we explained also previously, immediately when the reaction starts, the concentration of the product will start to decrease, making the forward reaction to also decrease. On the other hand, the concentration of the product will now start to increase, and the rate of the reverse reaction will also increase. After a certain time, the rate of forward and reaction is the same as the rate of reverse reaction, and at that point we are saying we have chemical equilibrium. Therefore, we are expecting, as the rate of as the rate of what reaction decreases and as the rate of the reverse reaction increases, we expect to say at a certain time, because this is a closed system, this system is isolated from its environment, nothing will go out, nothing will come in. Therefore, at a certain stage, the two reactions will reach what we call chemical equilibrium. And already we know what we mean by chemical equilibrium. We are just referring to say the rate of the forward reaction is equal to the rate of the reverse reaction. Therefore, it means the reaction hasn't stopped, but it has reached dynamic equilibrium. So it is very important that you understand what will happen at the beginning of the reaction and what will happen as the reaction reaches equilibrium. I think we already know that before the reaction can start, the only thing that you will have in your reaction are your reactants. You will not have products at the beginning of any reaction. However, when the reaction reaches equilibrium, then you will find both the products and the reactants being available in your reaction, because now they are operating at the same rate. The forward reaction and the reverse reaction has now reached an equilibrium. It is now operating at the same rate, meaning that the products are forming the reactants and the reactants are forming the product. That is very important. However, it is very important that as you start the reaction, you need to understand that this is exactly what is happening. This graph, we saw it in our previous lesson. However, in our previous lesson, remember, we never reached equilibrium because our system was open. We never have an isolated system as we are having right now. So what we have seen is that previously, we have seen that the number of reactants were just decreasing in terms of the concentration. And also the rate of the reaction was also decreasing. So that was the only thing that you're looking at, and the products were forming. But now, as the reaction rate of the reactants is decreasing, the reaction rate of the product is increasing. Remember, hydrogen and iodine gas, they are both our reactants, and their rate is decreasing as their concentration is decreasing. And what is happening with our product? Our product is increasing, meaning that as the concentration of the product is increasing, the rate of the reverse reaction is also increasing. So this part represents the forward reaction, and this part represents the reverse reaction. So what is represented by reverse reaction? The products are representing the reverse reaction as they are forming, and the reactants are representing the forward reaction as they are getting used up, as they are decreasing. Now, in this case now, instead of our reactants being used up, they are not going to be used up because this is a closed system, but they are going to reach what we call chemical equilibrium, whereby now the rate of forward reaction will be equals to the rate of the reverse reaction. By looking at this reaction, you can see that as hydrogen and iodine are forming hydrogen iodide in reverse is also forming hydrogen and iodine. Therefore, we are saying our system has reached equilibrium. Now, it is very important to understand, when do we reach equilibrium? What are the conditions of the reactants and the products to reach equilibrium? The chemical reaction must be reversible. The first thing that you must understand is that if you find that your reaction is irreversible, you cannot turn back the products back to reactants. You must understand that your reaction cannot reach equilibrium. So the first thing that you must understand about reaching equilibrium, you must understand that firstly, that reaction must be reversible, and the system must also be closed, meaning that you must make sure that your system is isolated from its environment. Therefore, that is the condition that your system will reach equilibrium. When a chemical equilibrium is reached in a closed system, the rates of forward reaction and the reverse reaction are the same, and the concentration of the reactants and the product will remain constant, meaning that at equilibrium, the concentration of the reactants and the products will remain constant. There will be no decrease and the increase of any of the concentration at equilibrium, unlike when we started the reaction. And when we started the reaction, we have seen that the concentration of the product was decreasing, of the reactants was decreasing, as the concentration of the product was increasing. But at equilibrium, both the concentration of the product and the reactants will be the same, will remain constant, will not change. So if the reaction reaches equilibrium, you can combine this concentration into an expression known as equilibrium constant. So we are going to look at how do we determine equilibrium constant at equilibrium. It is very important that you need to understand that equilibrium constant that we are going to look at with its expression will only occur when the system has reached equilibrium, where we have a isolated or closed system, whereby the concentration of the product and the reactants remains constant. Those are the conditions that can make your system to reach equilibrium. Now, this is an expression that we are going to use to calculate or to determine equilibrium constant. As I gave this example before of reactant A and B and product C and D, now we are going to write our product and our reactants in an equilibrium expression. The equilibrium constant always has the same value provided don't change the temperature, meaning that the equilibrium constant can be affected by temperature, meaning that is the condition that can affect equilibrium constant. So today our lesson will be mostly based on how do we calculate equilibrium constant, and as I said, how do we reach equilibrium, as I was explaining. Now, how do we calculate equilibrium constant, which has an abbreviation Kc? Equilibrium constant is equals to the concentration of the product divided by the concentration of the reactant, meaning that the product of the concentration of the product divided by the product of the concentration of the reactant. And you can see that the Kc, or the equilibrium constant, we use the square bracket to represent what we called concentration. It is very important that you write the correct expression of equilibrium constant, whereby you will use the square brackets to indicate the concentration at equilibrium of your products and your reactants. However, the reaction is say Kc is equals to the concentration of the product divided by the concentration of the reactants, in simple ways. And we are going to use these indexes as the exponents. If you can see, Na, okay, let me start with, because it's the product, the C, it becomes our product, and the number of moles of C becomes our exponent. And also the Y is there as an exponent, and D is there inside the brackets. Also, so our indexes are the numbers in front of each substance in the chemical equilibrium, and they will definitely be our exponents. So it is very important that you understand how do you calculate equilibrium constant and how do you write the correct equilibrium constant expression, making sure that always when you refer to the concentration, you are using square brackets and not round brackets. Now, I will just give you some time to look at this reaction and make sure that you also be able to move from the reaction to the expression. So this is our expression. And I also explained that this equilibrium constant can only be affected by the change in temperature and nothing else, unlike other factors that affected the previous reactions. But Kc can only be affected by the temperature. Let's go to our next slide. Now, before we're going to start calculating our equilibrium constant, I think it is very important that we look at our pre-knowledge in terms of the quantitative aspect of matter. Remember, as we are going to do these calculations, there is no way that we are not going to look at different quantitative aspects of matter. The first thing that you need to remember, as we are now in grade 12, you need to remember how did you calculate the number of moles starting from grade 10. We know that we calculate the number of moles by looking at the mass of a substance divided by the molar mass. Now, the mass will always be provided to you, or the units of mass are grams. And the molar mass will be always given the units grams per mole. Let me just do an example so that we remember how do we calculate the molar mass. Because mass, it is easy because we are definitely going to use the formula to calculate the mass or the number of moles. Let me just give an example of water. Let's say we calculate the molar mass of water. If we calculate the molar mass of water, remember, as we are dealing with chemistry, there is no way that we can not always refer to our periodic table, because we are dealing with atoms that are found on the periodic table. So we need to go back to our periodic table and look at the atomic masses of those atoms that are forming those compounds. So as we look at water, you can see that it's formed by 2 hydrogens and 1 oxygen. And when you go to the periodic table, you will notice that the number of moles, the atomic mass of hydrogen is 1, and there are 2 hydrogens involved, so it's 1 times 2, plus the atomic mass of oxygen is 16. Just refer to your periodic table. And at the end of the day, you'll find that the molar mass of water is going to be 1 times 2, which is going to give you 2, plus 16, which is going to give you 18 grams per mole. I am just reminding you so that you know that as we are going to start with quantitative aspect of matter and we are going to make some calculations under our topic of chemistry, we need to always go back and remember what information do we need for all calculations that we know in chemistry. We can also do the calculation of the molar mass of calcium carbonate. Calcium S is the element in group number 2 and element number 20 in the periodic table is having the molar mass of 14. Plus, carbon is our element number 6 in the periodic table, and we know that is having the molar mass of 12. So we know that we'll always refer to the molar mass or the atomic mass on our periodic table. So it is very important that immediately when you start with your calculation, make sure that you put your periodic table in front of you so that you make it handy for you in order for you to be able to refer to it. Then there are 3 atoms. This oxygen must be a capital letter. There are 3 atoms of oxygen in this calcium carbonate. Therefore, we know that for oxygen is going to be 16 multiplied by 3, and it will be giving us 48. So it means we have 48 for oxygens, the 3 oxygen, plus 12 plus 40. 48 plus 12 give us 60. And then 60 plus 40 give us 100. So it means calcium carbonate give us 100 grams per mole. This is the molar mass. This is 1. This is the molar mass of calcium carbonate. I just felt that we need to just go back a little bit and practice some of our quantitative aspect of matter, because we are now going to deal with calculations that will need us to remember some of the pre-knowledge that we did in our previous classes, as I promised previously. Now, we also need to remember how do we calculate concentration. I think we calculated concentration mostly in grade 11. So how do you calculate concentration? We need to understand, the first thing that you need to understand, that is why I started with number of moles. We need to know that concentration is the number of moles in mole divided by the volume in, it's incorrect. This is supposed to be decimeter cubed. It's not mole per decimeter cube, because mole per decimeter cube is the, these are the units of concentration. So it's decimeter cube with a positive 3 at the top. So these are the units to calculate volume. Volume is calculated with dm cube. So it is very important that immediately when you know that the units are in cubic decimeter and you are provided cubic centimeter, you need to know how do you convert back from cubic centimeter to cubic decimeter. And we always tried to explain it in our previous grades, especially in grade 11, to say, how do you move from cubic centimeter to cubic decimeter? So it is very important that we know how do we calculate concentration, because remember, we will be using concentration to calculate Kc. So the knowledge of calculations of concentration is very handy for us to go about in calculation the equilibrium constant, because we need to know how do we calculate concentration. And we also need to remember the units of concentration, of number of moles, and also of what? Of volume. So this is very important that you understand before you can start with quantitative aspect of any matter that you are going to look at in terms of our paper 2 chemistry. Now, I want us to look at this example. The first thing that I want to look at this reversible reaction of calcium carbonate. Calcium carbonate here is decomposing to calcium oxide and carbon dioxide gas. The first question that I can ask you is that, what is this system? Is this a homogeneous system or is this a heterogeneous system? As I explained, we are going to look at the phases of our reactants and product. And you can see that calcium carbonate is a solid, calcium oxide is a solid, however, carbon dioxide is a gas. So therefore, you can proudly say this is a heterogeneous system because our phases are not the same. Now, this example says to you, actually the equation was about write the Kc expression. Now, if you look at the Kc expression of this reaction, the reaction that is provided in front of you, I think I have explained on my previous lesson to say the concentration of all the solids is 1. Therefore, we already know that the concentration of solids is 1. Therefore, if we have to write the Kc expression, what are we going to do? We know that we will always write our Kc expression as the concentration of the product divided by the concentration of the reactant, which is very important. Now, when you look at our product, you can see now that our product is calcium oxide and carbon dioxide. And we know that according to Kc, it means it's going to be the concentration of calcium oxide multiplied by the concentration of carbon dioxide divided by concentration of calcium carbonate. Now you can see that I don't have any exponent because all these substances are having 1 mole, 1 mole, 1 mole each. So there is no need for me to write 1, 1, 1 as exponents because anything to exponent 1 is that thing according to mathematics. So there's no need for me to indicate the ones as exponents. Now, because now we already know our products, and then immediately when you look at this, you can see that now our Kc, because this is a solid, it means its concentration is 1, and then we have what? Carbon dioxide concentration. Divide also by 1. So you can see that at the end of the day, our Kc value will be equals to the concentration of carbon dioxide. So it is very important that you look at the phases before you write your Kc expression, because you need to know that the concentration of all the products is going to be 1. Therefore, if you substitute the concentration of the product, you know that you will substitute them by 1. So that is why at the end of the day, you'll find that your Kc now is equals to the concentration of carbon dioxide only, because the calcium oxide is 1 and also divide by 1 of calcium carbonate. Therefore, we already know how do we write Kc expression. Moving from Kc expression being the concentration of the product divided by the concentration of the reactants. And it is very important that you know how to correctly write this Kc expression. This actually is supposed to be a subscript, because the C, because of the constant, is a small c, and the concentration of the product, which is our carbon dioxide. And I made it a point that I write my concentration in square bracket because I'm looking at the concentration of carbon dioxide. When you look at our second example, you must also know that the concentration of the liquids is also 1. So the concentration of products and the concentration of liquids is 1. But aqueous solution gases, we can calculate the concentration. So if you have hydrochloric acid gas reacting with water, which is a liquid, giving you hydrogen ions, which are aqueous, plus chloride ions, which are aqueous. If you want to express this reaction in terms of Kc expression, we know that it's still going to be the concentration of the product divided by the concentration of the reactants. And you can see that now our product is this hydrogen ions and chloride ions. So it's the concentration of hydrogen ions multiplied by the concentration of chloride ions divided by the concentration of hydrochloric acid gas. Why was water not included? Remember, water in this state is provided as a liquid and its concentration is 1. So therefore, we just ignore it, because anything multiplied by 1 will definitely give us 1. So that is why the Kc expression is written as the concentration of the product, which is H2O plus concentration, multiplied by Cl minus concentration divided by HCl concentration. Now, what does the Kc value mean to you? After you have calculated the Kc and you find the value of Kc, what does it mean to you? Kc value, if the Kc value is greater than 1, I think we already know what is 1. If you find that you calculate the Kc or you calculate the equilibrium constant and you find that the equilibrium constant is greater than 1, you need to know that the forward reaction is favored. So that reaction will be favoring forward reaction. But if you find that your Kc is less than 1 or lower, that indicates that your reverse reaction is favored. So as we'll be calculating our Kc, we will be also referring to the Kc value. We'll also be explaining which reaction is favored in terms of the Kc value that we are going to find as we are going to calculate Kc. So you just look at the value of Kc. And what is important, you need to know that as equilibrium constant that is going to be calculated, there are no units. Meaning that if a question needs you to, it requires you to calculate equilibrium constant, you will write the value without units. Remember, the mole per decimeter cube are the units for concentration. The moles are the unit for number of moles. The decimeter cube are the units for the volume. So it is very important that you know that immediately when you find your Kc value, you don't write any units because Kc do not have units. If you put some units in your Kc value, definitely you are not going to get the correct answer. Let's look at this example. I will just give you 2 minutes just to do this example because actually this one, let's do it together because it's a first example that I'm giving you, and I've already made some solutions for you. We are going to use Kc expression to calculate Kc. As we know, how do we write Kc expression? Being the concentration of the product divided by the concentration of the reactants, and making sure that we don't forget that our indexes will become our exponents as we are going to write our Kc expression. Now let's look at this example. An equilibrium mixture of carbon dioxide gas, hydrogen gas, and carbon monoxide gas and water at 100 degrees Celsius is analyzed, and it is found that the concentration of carbon monoxide is equal to 3 moles per decimeter cube, water 7.2 mole per decimeter cube, carbon dioxide 2.4 mole per decimeter cube, and hydrogen gas 4.5 mole per decimeter cube. So what the examiner has given you here, the examiner has given you the concentration of all your products and all your reactants. The only thing that you are required to do, you are required to calculate Kc. So how are we going to calculate Kc? The first thing that we need to know, we need to be able to write a balanced chemical equation for our reaction, whereby we know that our carbon dioxide will react with hydrogen gas to give you calcium oxide and water. At the same time, carbon monoxide. At the same time, carbon monoxide gas can react back and give you carbon dioxide and hydrogen. Why am I saying that? Remember, this is a reversible reaction. How do you see that this is a reversible reaction? By the double arrows going forward and backward. Now, how do we do it? How do we calculate Kc? We know that carbon monoxide and water, remember, in this case, water is now a gas, unlike the previous example where water was a liquid. So as a gas, it will be able to have concentration. So that is why we consider the concentration of water as a gas. So that is why we can calculate the concentration, or we can know the value of the concentration of water as a gas, but not as a liquid, because as a liquid, the concentration is 1. And we also explain that all solids have concentration, which is 1. So the concentration of our product, which is carbon monoxide and water, divided by the concentration of carbon dioxide and hydrogen gas. So all the values were provided to us. We know that carbon monoxide is 3, which is multiplied by 7.2 of water, divided by 2.4 of carbon dioxide, multiplied by 4.5 of hydrogen gas. Then, after multiplying the product and dividing with the reactant's concentration. Therefore, you are going to get your value of Kc. Now, you can see that as I wrote the value of Kc, I didn't put any units because Kc value do not require you to have any units. Therefore, you need to make sure that after writing your Kc value, you check whether you didn't make a mistake by putting units, because I know we are so used in writing units, and we make sure that always we write units because we know that our answer will not be correct if there are no units. But make sure that in this case, you don't put any units, because units are not allowed when you are calculating what Kc, because equilibrium constant doesn't have units. Actually, it's because the concentration will cancel each other. Remember, we have mole per decimeter cube at the top. We have also mole per decimeter cube at the bottom. And this mole per decimeter cube and the mole per decimeter cube will cancel each other. And at the end of the day, we are not going to have any units for Kc. That is the main reason why Kc doesn't have units. Now, when you look at the value of Kc, you can see now that the value of Kc is 2. The second thing that you need to ask yourself is my forward or reverse reaction favored? By looking at the Kc value, you can tell, because it is very significant that you know that what does the Kc value means to you, because as we move forward with this topic, we will look at how will the forward and the reaction, how will the forward and the reverse reaction be favored. So the Kc value will already tell you which type of reaction is favored between forward and reverse reaction. So because the Kc value is greater than 1, it means now the Kc value is greater than 1. As I explained in my previous slide, if the Kc value is greater than 1, it means forward reaction is favored. Therefore, for this reaction, we can safely say the forward reaction is favored, because we have looked at our Kc value. Now, I am going to give you another example where we look at how do we calculate Kc values. And what I'm going to do now, I'm going to give you some time for you to check on how to calculate Kc value. But for the first example, because this is an example that will assist you to know how do we calculate Kc value if few information is provided to us, but not forgetting that all the pre-knowledge of quantitative aspect of matter in terms of the calculations is very important. Let's look at our second example, which I'm going to make it with you also. I'm going to do the second example with you. Now, we have a mixture of 0.3 moles of hydrogen gas and 0.2 moles of oxygen is placed in a closed container with a volume of 200 cubic centimeter. Immediately when you can look at the volume, you can see now that our volume is provided in terms of cubic centimeters. Therefore, what is it that must come into your mind? You must firstly just ask yourself, how do I convert my volume to cubic decimeters? We know that if we are having cubic centimeters, we divide them by 1,000 for us to get cubic decimeters. Therefore, it is very important that immediately you just convert your volume, because you know that at the end of the day, you will be dealing with concentration. And how are the units of concentration being calculated? The units of concentration are moles per decimeter cube, or are moles per cubic decimeter. Therefore, you definitely need to convert your cubic centimeters into your cubic decimeters. Therefore, you will know that if you say 200 divided by 1,000, you will get something like 0.2 cubic decimeter. Therefore, you already converted your volume, because it is always safe to work with correct units immediately when you are doing what calculations. And as long as you know which quantities are you dealing with. In this case, we are dealing in terms of concentration. So therefore, we need to convert and everything that has to do with concentration in terms of the required units of concentration. Now, they say this reaction reaches equilibrium. So this reaction will reach equilibrium. I think by now we already know what do we mean by equilibrium. We already know what do we mean by chemical equilibrium. So it will reach the chemical equilibrium at this temperature of 50 degrees Celsius. And as I said on my previous slide, as I was explaining equilibrium constant, I said the only thing that can change the value of equilibrium constant is temperature. So make sure that you keep, if you don't want to change the equilibrium constant, you make sure that your temperature remains constant, because any change in temperature will definitely affect your values of Kc. Therefore, and there is 0.1 mole of hydrogen left in the container. Determine the equilibrium constant of this reaction. The first thing that I want to explain before I go to the solution, I think at this point in time, we know that as we start the reaction, before anything can occur, we know that the only things that we have are the reactants, and we don't have a product. So it is very important that you know what you have initially when you start your reaction. And you need to know what are you going to use and to produce at equilibrium, and what will be your concentration at equilibrium, and then you can calculate the concentration at equilibrium, your Kc. So the reaction is very important because certain number of moles of reactants will react and certain number of moles of product will also be formed during your reaction. So it is very important to remember your mole ratio issue that you did last year in grade 10 and 11, because the mole ratio will play a very important role in calculations of Kc, because we are using a quantitative aspect of matter. If you look at this reaction as you are provided, you can see that 2 moles of hydrogen gas react with 1 mole of oxygen gas to form 2 moles of water. That is the ratio in which the reactants and the product are reacting with each other in this reaction. Therefore, it is very important that you understand the mole ratio, meaning that if I have 2 moles of hydrogen, 1 mole of oxygen, giving me 2 moles of water. If I have 4 moles of this, it means I will have 2 moles of this and I will have 4 moles of this. The mole ratio plays a very important role because you will know how are the reactants and products reacting according to their hypothetical reaction. Therefore, you need to always take into cognizance when you know the number of moles of one of the substance in the reaction. Using the mole ratio, you can determine all the other number of moles. If maybe I'm having 0.6 moles like of this a hydrogen, it means I will be required, I will already know that there will be 0.3 moles of this one reacting and 0.6 moles of this one for me. Remember, these are your reactants and this is the product. And initially, you will only have your reactants, and finally, you will also, at the end, at equilibrium, you'll have both the reactants and product. But as you initially start your reaction, definitely you'll have what we called reactants. Now, let's look at this, because this one I want to do it with you, as we are going to use this table method in order to determine the Kc value by looking at what we had initially, what is used, and what the number of moles of at equilibrium and the number of moles at the concentration at equilibrium. So it is important that you understand this table very carefully, and it is also important that you are labeling this table correctly, because this table will give you the information that you need as you are going to calculate your equilibrium constant. Because for you to calculate equilibrium constant, which is Kc, what is it that you need? You need the concentration of the product and the reactants at equilibrium. However, in the reaction that you are provided, or in the information that you are provided, as an example, we are not provided the concentration of product and the reactants at equilibrium. We need to firstly find those concentrations so that we can use the equilibrium expression to calculate equilibrium constant. Therefore, how can we be assisted with this table method in order for us to find the concentration at equilibrium that will make us to calculate equilibrium constant? Now, as I have the statement again on this slide, we are going to look at our table now. The first thing that I said you must look at mole ratio. So the first thing you must look at how the reactants and the product are reacting with each other in terms of the number of moles. So we look at the mole ratio. What are we having? We are having hydrogen, we are having oxygen, we are having water. So in which ratio are they reacting? For every 2 moles of hydrogen, we have 1 mole of oxygen and 2 moles of water are going to be formed. So initially though, so this is the first part is about the ratio of the reacting substances and the product being formed. So The first thing that we're going to look at, we are going to look at initially. What do we have initially? Initially, we are provided 0.3 moles of hydrogen and 0.2 moles of oxygen. What is hydrogen and oxygen? Hydrogen and oxygen are our reactants. That is what we are having initially. Do we have any product initially? Definitely not. We know that initially the number of reactants that we have, and then it will be reacting, decreasing the concentration in order to give us the product, or decreasing the number of moles in order to give us the product. So we have 0.3 initially at the start. We can say start or initially. We have 0.3 moles of hydrogen. We have 0.2 moles of oxygen, and we don't have any number of, we have 0 moles of product, because this is our initial state of the reaction. Then the number of moles used or produced, here now is where we are going to use our mole ratio. Our question says, at equilibrium, when the reaction reaches equilibrium, we are left with 0.2 moles of, and where is the equilibrium is the next stage. So here we know that we need to use the hydrogen and the oxygen to get water. So we know that we lose 2 number of moles of, that's why I'm using X. X represents the number of moles of hydrogen and 1 number of moles of oxygen to get 2 number of moles. And you can see that I'm using minus, because remember, those number of moles are going to be used up. They are going to decrease from the initial one, subtract the final one. So it is very important that you know that at the point where we are dealing with the used or produced, the reactants are going to be used, whereas the product is going to be produced. So the used and produced represent that part of the reactants being used or produced. And that's where we are going to use our mole ratio, because they are going to be used and being produced according to the ratio in which they are reacting with. I think it is very important that you understand that part. So we are just told that, and then after that, after number of moles used or produced, we need to know the number of moles at equilibrium. And the last thing, we need to know the concentration at equilibrium. That will assist us to calculate Kc. So when you look at the information that we're given, you can see now that at equilibrium, we are told that there are 0.1 moles of hydrogen gas left. Therefore, it means hydrogen started from 0.2, and we find that at equilibrium, we find 0.1. Therefore, the first thing that you ask yourself is, how much was used for this hydrogen to, for this, where is it, hydrogen? Yeah, here is hydrogen. I'm sorry about using this one. For this hydrogen to be left with 0.1, it started with 0.3, and at equilibrium, it is found to have 0.1. It means from 0.3, for you to get 0.1, it means 0.2 moles were used, because you are going to say 0.3, which is your initial number of moles, subtract 0.1, which are the moles left inside your container, to get 0.2 moles. Therefore, it means the number of moles of hydrogen that were used, or that was used, it was 0.2. So it means here for hydrogen, you know that we have 0.2 moles being used. Therefore, how do we find another number of moles of oxygen and hydrogen? We go back to our mole ratio to say the reaction in terms of the ratio is 2:1:2. Therefore, if I use 0.2 moles of hydrogen, it means I will use, because the ratio is 1:2:1 with oxygen, it means I will use 0.1 mole of oxygen, and I will get what? I will get, you already know how many moles that are you going to get here, because remember the ratio is 2. So it means there will be 0.2 moles that will be found at equilibrium, the moles that will be produced when you are using 0.2 and 0.1 moles of the reactants to form that product. Initially we had 0, but after that you produced 0.2. Therefore, it means now as you go further, initially for hydrogen you had 0.3, you use 0.2, and then you find 0.1 at equilibrium. Therefore, you can now safely say that, because now I know the number of moles that I have used for this oxygen gas, I was having 0.2 and I have used 0.1. It means at equilibrium I will also have what? 0,1 number of moles, because we're going to say 0,2 subtract 0,1, and at equilibrium we're going to get 0,1. It is very important that you use this mole ratio, because how are you going to know that it's 0,1 that is going to be used? The only thing that will tell you how do you know that it's 0,1 is through using the mole ratio, because you already know the number of mole of one of the substances that is reacting with oxygen. Then initially we had 0, but now we find that we have 0,2. So it means 0,2 was the number of moles that was produced as hydrogen was reacting with oxygen to give you water. So 0,2 moles of water will be produced. How do we know that is 0,2? Remember, the ratio is 2:2 with what? With hydrogen. That we have discovered is number of moles as 0,2. Therefore, at equilibrium, what do we have now? We have 0,3 subtracting 0,2, which is 0,1. We have 0,2 subtracting 0,1, which is 0,1. And then we have 0 and then plus 0,2. Remember, we are adding because we are forming a product, because the product is added as it is forming, it is increasing, because it was not there. Initially, we had 0. So 0 plus 0,2, and we are going to get 0,2. So now we have our number of moles at equilibrium. What is left now is to find the concentration at equilibrium. Remember, the volume at equilibrium, the volume was provided to us as 200 cubic decimeter, and we made it a point that we convert it to 0,2 cubic decimeter. Therefore, how do we calculate concentration? As I reminded you in our previous concentration is calculated as C is equal to N over V. What concentration are we calculating? We are calculating concentration at equilibrium. Therefore, we already know the number of moles at equilibrium, and we know the volume at equilibrium. Therefore, we just say 0,1 divided by 0,2, which will give us 0,5 mole per decimeter cube, which is the concentration of hydrogen. And then 0,1 divided by 0,2 will also give another 0,5 mole per decimeter cube. And then 0,2, which is going to be divided by 0,2, is going to give us 1 mole per decimeter cube of what? Of water. So already now we are having our concentration at equilibrium. The next thing that is left now, I'm going to give you 2 minutes just to find the equilibrium constant after you have discovered the concentration at equilibrium. So I will make sure that I give you just 2 minutes to calculate Kc for our reaction. Just for 2 minutes break. Welcome back, grade 12s. I hope you were able to calculate our Kc value. Remember, learners, this lesson is proudly brought to you by Gauteng Department of Education in collaboration with Saibono Discovery Center, and it is streamed by Pagama Research and Development. As I said when I started, you can interact with us on 064 748 8913. Now, what is it that we're doing? We went through all this trouble just to calculate the concentration at equilibrium, because there is no way that we can calculate Kc without knowing how to calculate the concentration at equilibrium. And the examiner in this case never gave us the concentration at equilibrium, but only gave us the number of moles and the volume. And the examiner only gave us the number of moles initially and the number of moles of one of the reactant at equilibrium. So we have to use what we know or what we have to find what we didn't have. So all that we're doing, we're just trying to find the concentration at equilibrium. Now, because we know the concentration at equilibrium, the next thing now is to write our Kc expression. Now, looking at our reaction, I think you have seen that our water was our product and our hydrogen and oxygen was our reactants. So for you to be able to calculate Kc, you need to write the correct Kc expression of the concentration of the product divided by the concentration of the reactants. And we have seen that our water was having an index of 2 and our hydrogen was having an index of 2 and oxygen was having only the index of 1. So our indexes became our exponent. So you must make sure that you don't forget to put those exponents, because definitely if you don't put them, if you miss them or if you omit them, it means your calculation will not be correct. So from the previous information that we have seen that for hydrogen you have 5 mole per decimeter cube, for oxygen you have 5 mole per decimeter cube, and for our water, which is our product, we have 1 mole per decimeter cube. So therefore, in terms of our Kc expression, we're going to put the concentration of hydrogen, which is 1 squared, and then divide by 0.5 squared, which is for hydrogen, and multiply by 0.5 squared, which is for oxygen. And then when you calculate using your calculator, you are going to calculate and get something like 8. Now, if you look at our Kc value, you will see that our Kc value is greater than 1. Therefore, I explained that if the Kc value is greater than 1, it means our forward reaction is favored. Which one is our forward reaction? Our forward reaction is the reaction of hydrogen and oxygen, meaning that now our forward reaction will be favored as compared to the reverse reaction. So the arrow will be longer going forward and will be smaller going backward to indicate that our forward reaction is favored. So it is very important that you understand this table. I know it's for the first time you are seeing us using the table, and always make sure that the table method is handy to you, especially when you are provided the number of moles, because it will assist you. Very important again, you need to know what makes you to calculate equilibrium constant. We were not going to go through all these steps if we knew the concentration at equilibrium. But we didn't know the concentration at equilibrium. And the only thing that we knew at equilibrium was only the number of moles of one of the reactant, which was hydrogen. So the number of moles of hydrogen at equilibrium is the one that assisted us to go back and check the number of moles, or to find the number of moles of other reacting substances in our reaction in terms of using the mole ratio. So we started by the mole ratio, and then we said the number of moles that are at equilibrium will subtract the number of moles, or the initial number of moles that we had initially, will subtract the number of moles at equilibrium, so that we can get the number of moles of the reactions that are being used. And we use the mole ratio to find the number of moles of other substances that were part of the reaction. And that is why we ended up getting 0.1 and 0.2 as our oxygen moles and as our water moles. And then after that, having the volume, we make sure that we divide all the number of moles at equilibrium with the volume. Make sure that you don't divide the number of moles that are used or produced, but you divide the number of moles with the volume that are at equilibrium. Because for you to be able to calculate Kc, you need to know the concentration at equilibrium. Now, I want us to go to the next example. For this one, I'm going to give you, because I want you to just try and use the table method that I just shown you right now to check whether you can be able to calculate our equilibrium constant. what is the information that is provided to you? I always say, use what you have to find what you don't have. So immediately when you are provided something as part of your statement, you need to know that you need to use that information on the statement to get what you don't have, so that you can be able to calculate what is required in your question. So let's look at our question. During a research experiment carried out by initially adding 1 mole of oxygen gas and 1 mole of nitrogen gas in 2 cubic decimeter closed container at 300 kelvins, it was found that the concentration of nitrogen oxide gas present in the container at equilibrium was 0.1 mole per decimeter cube. So what is it that we are provided? In terms of our data, we are provided the mass of what? We are provided the number of moles of oxygen initially, which is 1 mole. We are provided the number of moles of nitrogen initially, which is also 1 mole. And we are provided the concentration at equilibrium of nitrogen, which is our product of nitrogen oxide gas, which is 0.1 mole per decimeter cube. Now, we know that for us to be able to calculate the Kc value, or to calculate the equilibrium constant, we need to know the concentration of both the reactants and the product. In this stage, the examiner has just given us the concentration of the product. Now, the next thing that we need to do, we need to say, how then do we go about finding the number of moles of the reactant, so that we can be able to calculate the concentration of the reactants at equilibrium? So I'm just going to give you 3 minutes for this one, to use that table method again, in order for you to calculate the number of moles, to calculate the equilibrium constant by finding the number of moles at equilibrium with the given volume of 2 cubic decimeter. So this one, definitely I will give you 3 minutes, so that you try the entire question, so that when you do the solution, you can see where are you not going right, in order for you to be assisted going forward. So the 3 minutes will start now for this question. Okay, welcome back, grade 12s. I'm having two questions from our WhatsApp group. As I said, you can interact with us using your WhatsApp. I'm having a question from Lisiko Ramuki. Lisiko Ramuki asks that what does it mean when we say the reactants are constant? We never said the reactants are constant, but we said the concentration of the reactants and the product at equilibrium are constant, meaning that the concentration of the reactants will no longer decrease or increase. The concentration of the product will no longer increase or decrease. So the concentration of the reactants and the product at equilibrium will remain constant. And the next question says, please give the example about concentration and time graph when it reaches equilibrium. As I said, to say at equilibrium, when we start with our reaction, let me just show you this this example that I was giving of the graph. Okay, here is the graph. I said, okay, let me go back a little. Okay, I said as the reaction starts, the concentration of the reactants will decrease and the concentration of the product will increase. And at equilibrium, the concentration of the reactants and the product will remain constant, meaning that the concentration of the reactants and the product will no longer change because it was changing all along before it reaches equilibrium, but at equilibrium the concentration doesn't change. So I hope learners, with these responses, you have understood what we mean by the questions that you have asked. And thank you so much for asking such questions, because sometimes the graphs questions are really confusing and you will end up not understanding what we mean by constant. By constant, we mean the reaction will not change or the concentration will not change. Now, what is it that we are provided? This is the solution that of our previous activity that we just had now. I hope the time was not sufficient enough for you to complete, but what I wanted you to get for this question, actually, I wanted you to go through the table, because the table is very important for you to understand how do you calculate the concentration at equilibrium. In this case, something else was asked, not exactly the same way the first question was asked. In this case, we were provided with the concentration of this substance, which is our product at equilibrium. 0.1 was provided at equilibrium as the concentration. So now, what do we do? As I started to say, we start with the ratio first. The ratio of these reacting substances is 1:1:2. So for every 1 mole of nitrogen, there will be 1 mole of oxygen reacting, and there will be 2 moles of nitrogen oxide gas forming. Therefore, the ratio is 1:1:2. What is the ratio that we are referring to? We are referring to the ratio of the product and the reactants. Now, initially, we are told that we have 1 mole of nitrogen gas, we have 1 mole of oxygen gas, and as usual, we don't have any product because initially there are no products, only reactants are there in a reaction. Therefore, we are told that at equilibrium, it is found that there are 0.1 moles of moles per decimeter cube of nitrogen oxide. Therefore, if we know the number of moles at equilibrium, if you know the concentration at equilibrium in terms of the nitrogen oxide, we can know the number of moles of nitrogen oxide at equilibrium. So now we need to use the information that we are provided at equilibrium to calculate the number of moles of nitrogen oxide at the beginning. So we know that, how do we calculate? We know that C is equals to N over V. Therefore, we are given the concentration as 0.1, which is equals to the number of moles we don't know at equilibrium, but we know that the volume we are provided as 2. Therefore, when we cross multiply, number of moles of this at equilibrium is going to be 2 multiplied by 0.1, which is going to give us 0.2 moles. So we already know the number of moles of nitrogen oxide at equilibrium, as we were provided the concentration at equilibrium. Therefore, if we know the number of moles at equilibrium, we know that we started with 0. However, we ended up with 0.2 moles at equilibrium. It means we have formed 0.2 moles that are being formed when the nitrogen reacted with the oxygen. Therefore, we now know the number of moles produced. These are the number of moles produced. Then how are we going to get the number of moles that reacted or that were used to produce this 0.2? Now it means now we are going to use mole ratio, because the mole ratio says 1:1:2. If we have 0.2 2 moles of nitrogen oxide, it means according to the ratio of 1, we'll have 0.1 mole of oxygen and 0.1 mole of nitrogen. Therefore, we already know the number of moles of nitrogen and oxygen that are being used for us to get 0.2 moles of what? Of nitrogen oxide. Therefore, after understanding that we know the number of moles that are being used, then we know the number of moles initially, we know the number of moles that are being used. We know the number of moles initially, we know the number of moles that are being used. So for us to find the moles at equilibrium, we are going to say the initial number of moles subtract the number of moles that are being used, and we are going to get 0.9 and 0.9 moles of what? Of nitrogen and oxygen, as their ratio is 1:1, and they were reacting almost exactly the same in terms of their mole ratio in our reaction. Therefore, we now know the number of moles at equilibrium. Then we can now calculate the concentration at equilibrium. Sorry about that. We can now calculate the concentration at equilibrium by using C is equals to N over V, whereby 0.9 is the number of moles of nitrogen divided by 2, which is the volume at equilibrium, and then also 0.9 divided by 2, and we get 0.5 mole per decimeter cube, and also 0.5 moles per decimeter cube of both our reactants. Then now we know our concentration at equilibrium. Immediately when you know our concentration at equilibrium, the next thing that you do, we now write our Kc expression, which is what will make us. So how do we definitely provide marks, or how do we award marks here? The first thing you need to, by using this information to get here, is 1 mark, and also by using the mole ratio is another mark. By calculating this is another mark, and also by calculating the concentration at equilibrium is another mark. So for the table only, we can get 5 marks. The 5 marks that will qualify you to even make it better in this question. So make sure that always you write your expression correctly, and you make sure that you write your table correctly by labeling it correctly. So the next thing, as I said, because we have our concentration, we're gonna go and write our Kc expression. Our Kc expression, as we know, is the concentration of the product divided by the concentration of the reactants. And remember, our product was having 2 as our number of moles or our index, so it means it will become our exponent. So it's going to be nitrogen oxide concentration squared divided by nitrogen concentration multiplied by oxygen concentration. And then because we know the values of those concentration, we just put them and we get our answer as 0.049. And if you look at this answer, you can see that now our answer for our Kc is now less than 1. So what does the less than 1 answer mean in terms of the Kc? It means now our reverse reaction is favored. Therefore, our reverse reaction in this reaction is going to be favored, and our forward reaction is going to have a smaller arrow, showing that the reaction is moving towards the reverse reaction, is the one that is being favored in this. Learners, I think it is very important that the table that you are going to write will be labeled correctly, so that you know exactly what you are doing, starting with the number, the mole ratio, what you have initially, what you have used or produced, the number of moles at equilibrium, and the last thing, the concentration at equilibrium. Because all what you are doing, you are trying to find the concentration at equilibrium so that you can be able to use your Kc expression to calculate equilibrium constant. We are going to go to this last example for the day, whereby now when you can look at this example, number 3, it is given that the thermal decomposition of calcium carbonate is an example of heterogeneous equilibrium. I think by now we understand what do we mean by heterogeneous system. And then the decomposition that takes place in a closed container can be represented by the following equation. Calcium carbonate, solid, giving you, and also giving back calcium oxide, solid plus carbon dioxide. So already we can see the phases are not the same. That is why this is referred as the heterogeneous mixture or heterogeneous reaction. Now, initially 5 grams of calcium carbonate solid is placed in a closed 500 cubic container and then heated. Equilibrium is reached at 900 degrees Celsius. Calculate the mass of unreacted calcium carbonate solid that remains in the container at equilibrium. I am going to go through to this question with you, because if I can give you time to make this question, we are not going to reach the end, because we are only left with very few minutes to end this lesson. I want us to go through this information that you are provided. When you look at this question, you can see that you are provided the mass of calcium carbonate, and you need the mass that never reacted, meaning that if they are saying the mass, a certain mass of a substance have not reacted, it means from the information that we had last year in grade 11, it means our calcium carbonate is our excess reactant. It never reacted all of it, meaning that it was not used up. So there was some excess moles or excess mass that remained in unreacted in this reaction. But what is important is that always when you are provided with mass, because we've been using number of moles in all the examples that we've been using, just try immediately and change the mass to the number of moles, so that immediately you can be able to start and knowing what we are dealing with. So the mass that you are provided the 5 grams, and you know that the molar mass of calcium carbonate, as we made an example in our previous example, it was 100. So the first thing that you know that is you are going to calculate the number of moles of calcium carbonate as N is equals to M over molar mass. And then you know that is going to be N, which is equals to 5 divided by 100. So you will be able now to calculate your number of moles. So you'll get the number of moles of calcium carbonate. Now, after getting the number of moles of calcium carbonate, the next thing that you have, you are provided the volume, but also you see that your volume is provided as cubic centimeter. So you know that you're gonna say 500, and then you're gonna divide it by 1,000, so that you get the cubic decimeter, which is gonna be 0.5 cubic decimeter. Then you now have the number of moles of calcium carbonate. You now have the number of moles of you have now the volume of the calcium carbonate that is reacting. Therefore, you are just looking for the mass that never reacted in this reaction. Then you are told that the equilibrium constant for this reaction is given as 0, so this time the examiner doesn't want you to calculate Kc, but the examiner has provided you with Kc. So how do you know how to write the Kc expression? How do you write the Kc expression? We know that the Kc expression will always be the concentration of the product divided by the concentration of the reactant. And as you look at the Kc concentration of the product, you can see that now Kc will be equals to the concentration of carbon dioxide. Why Kc is equals to the concentration of carbon dioxide only? Remember, calcium carbonate is a solid, and also calcium oxide is a solid. So we know that the concentration of our solid is 1. Therefore, it ends up being the concentration of this, the equilibrium constant being equals to the concentration of carbon dioxide. And we know that the examiner has provided us with the equilibrium constant. Therefore, our Kc, as we substitute it, is 0.0108, and therefore, which is equals to the concentration of carbon dioxide. So we now know the concentration of carbon dioxide. The concentration of carbon dioxide is equals to 0.0108 moles per decimeter cube. So already we know the concentration of carbon dioxide, and if we know the concentration of carbon dioxide, we can be able to find the number of moles of, because we are looking for the unreacted calcium carbonate. How is carbon dioxide related to calcium carbonate? Carbon dioxide is related to calcium carbonate using the mole ratio. Therefore, if we can be able to calculate the number of moles of carbon dioxide that will be formed, we will be able to find the number of moles of calcium carbonate that was decomposed, in order for us to see how many number of moles were used for us to get this. So therefore, we are going to say, as we are going to use the C is equals to N over V, which is our formula for calculating the concentration. C is equals to 0.0108, which is the carbon dioxide, multiplied by 0.5, which is for what? The volume of the container. Therefore, we get the number of moles of carbon dioxide as 0.045. And we know that according to the mole ratio, 1 mole of calcium carbonate give you 1 mole of carbon dioxide. Therefore, the number of moles of calcium carbonate are equals to those number of moles of carbon dioxide. And knowing the molar mass, we can be able to find now the mass that reacted. So because now we know that the mass that reacted, and we were told that initially we were given 5 grams, but only 0.5 only 0.454 grams reacted. Therefore, it means 4.46 grams of calcium carbonate didn't react. So, learners, you need to know the information that you are given so that always you use the previous information that you have in your lesson in order for you to make sure that you use what you have to get what you didn't have. By so saying, I would like to say we have come to the end of our lesson. Make sure that you go back to what we did, because this is our YouTube channel. You can even go back and check what we've been doing, and make sure that you follow up to what we've been doing so that you can see how do we calculate this KC and how do we use the information that we have in order to find the information that we don't have. By so saying, I would like to say we have come to the end of this lesson. Thank you so much for watching this lesson, and make sure that you keep safe all times, and make sure that you always interact with us with whatever information that you want to know in terms of these topics that we are dealing with in our streaming line. By so saying, I would like to say thank you so much for watching this lesson. My name is Thandwe Uwane again, and this lesson was brought to you by Gauteng Department of Education. By so saying, I will say thank you so much and goodbye for now.